So I'm going to do a single stoichiometry problem with a lot of questions based upon one starting quantity of one reactant. So this is the combustion of butane. So for every 2 moles of butane, this is butane over here, you would need to consume 13 moles of oxygen and make 8 moles of carbon dioxide and 10 moles of water. Now above each of those formulas, I put the gram formula mass, so the mass of 1 mole, because we're going to use those to do our math, and I figured that's what we don't want to spend our time on, because that's relatively easy. So the question states that we have 2.7 liters. I'm going to put a little 0 in there to give us an extra significant digit on this. All right, so we'll have 3 sig figs of C4H10, and STP is completely combusted. And then I ask the following questions. How many grams of H2O are produced? How many molecules of water? How many liters of water? And they ask for the grams of liters of oxygen consumed at STP. Let's handle the grams of water produced first. Now, what I also want to point out here is the critical thing is to keep track of moles. So I'm going to pause whenever I get the moles of something, because that's going to be something I can use to solve a problem later. So let's start off. We have 2.70 liters of C4H10. The first thing we want to do is convert that to moles. So we know by now, as long as it's at STP and it's a gas, and butane is in fact a gas, that for every 22.4 liters, we have 1 mole of this stuff, C4H10. And when you do the math here, what you get is 0.12053 mole of C4H10. Now, let's be aware, this is not rounded to the right number of sig figs. If this was rounded correctly, it would be 0.121. But I'm going to keep the 53 here because I'm going to round everything when I'm done and I get the answers. And when I do round them, I'm going to round them to 3 significant digits. So the first question is, how many grams of H2O are produced? Well, the ratio of moles of C4H10 to water is a 2 to 10 ratio. So for every 2 moles, okay, of C4H10, I get 10 moles of water. And basically, that's 10 over 2. I'm basically multiplying this number by 5. And when I do that, I get 0.60265 moles of H2O. Now, if I want to know the grams of that, essentially, I'm just going to take that thing and I'm going to multiply it by 18.016 grams is 1 mole of water. And that gives me 10.8573 grams of water. And I'm going to cut that off right there. So my final answer is going to be 10.9. All right. I want to circle a couple of things here because I want you to recognize this. Now that I know how many moles of water I'm going to make and how many moles of butane are going to be consumed, I can directly use the ratios in these 2 numbers that I boxed to answer any of the other questions I want. I'm not going to want to use this number here for anything else, but I could use either one of these to get the correct answer. So, number of molecules of water produced. Well, I could start all the way back here and start over again, but since I already know the moles of water, why bother? I want to make my problems as fast as possible. You know how they get you on the AP exam? Time. If you know how to cut out steps logically and rationally, you're going to be able to finish the exam. And I'll be honest with you, I'd say probably a good solid third of the people who take that exam across the country can't finish it in time. So we can just take our 0.60265 moles of H2O and basically go, oh, how many molecules? Well, for every 1 mole of H2O, right? I've been kind of lazy about canceling. I'll do it now. I'm going to have 6.022 times 10 to the 23rd molecules. And when I do the math here, the moles of water cancel out, and I get, let's see, 3.2. I'm going to round this one to 3 sig figs now, just to save us some time, to 3.63 times 10 to the 23rd molecules, okay, and that's molecules of water. Liters of, now I can do the same thing with liters of water. I can use this number up here again, right? if I needed atoms of hydrogen, I could take this number that I just got here and multiply it by 2. There's lots of things I can do as long as I understand what are the proportional relationships that I use in stoichiometry. So for this, I can go 0.60265 mole of H2O, and I can go for every 1 mole of H2O, right? I have 22.4 liters of H2O, as long as it's at STP. And so I can multiply that out again, and I get a number of like 13.49, so it's going to be 13.5 liters. Now, one of the things I want to show you here is for this one in particular, and that's liters of H2O, okay, there's something really important to recognize. I don't have to go through a lot of work when I'm dealing with volume-to-volume problems. Because the volume of a liter of a mole is always 22.4, the ratio of the volumes is the same as the ratio of moles. So I can literally, if I had taken 2.70 liters, and if I look at the ratio, there's for every 2 moles of this stuff, there are 10 moles of, if I take this and multiply it by 5 in my calculator, you know what I get? 13.5 liters. And the reason why is because the mole ratio and the volume ratios are exactly the same. This shows up in a lot of multiple choice questions. So you can kind of skip it and not do any really tough math, knowing that the volume ratio for gases, and gases only at STP, okay, well, it doesn't have to be STP, as you keep the conditions the same. The volume ratio is the same as the mole ratio for gases, as long as the conditions are constant. All right, so we can do the same thing with the grams and liters of oxygen consumed at STP. Now, some students struggle with the idea. If you figure out how much is produced, you can also figure out how much is consumed, because for every 2 moles of C4H4 that is consumed, 13 moles of oxygen are also consumed, if everything is being, So, we can start off kind of the same way. We can start off with this number right here. And I'm starting with this number right here because why bother going back I could also have used this number over here again, right? Whichever one works more easily for me. Neither one is a nice, neat ratio, so I'm going to stick with the C4H10. Okay, so if I have 0.12053 moles of C4H10, and I want to know how many moles of oxygen is being consumed, well, I know that for every 2 moles of C4H10, I'm going to have to consume 13 moles of O2. Basically, for every 1 mole of C4H10, 6.5 moles of oxygen. And I can easily multiply that out, and I get a big number, 0.78348. And that's my moles of O2. All right. I can now use this number 2 ways. I can use this number and get the grams of oxygen, because I can multiply this by 32 grams, that's 0.00, is 1 mole of oxygen. Or I can for volume, I can say for every 1 mole of O2, there's 22.4 liters. And of course, again, if I multiply 2.70 by 6.5, that's going to give me the exact same number I'm going to get right now. You should check it with your calculator. But I get, when I do this multiplication, and again, these cancel out, I get 2.507 grams of oxygen, and I get 17.55 liters. And if I take my calculator and divide this by 6.5, it gives me 2.70. Sig fig wise, we're going to round it here, so right here, so it's really 2.51 grams, and this would be 17.6. I'm not so focused on the sig figs. The key thing is to make sure that anything that's not an exact number, you take it out as many places as you can, so that in the end you can round to the right number of sig figs.